Safety means the class or a method behaves correctly when accessed by multiple threads simultaneously. A thread-safe component prevents unintended interactions even if several threads operates on the same data. So thread safety is crucial in multi-threaded Java programs to avoid issues like data corruptions, race conditions, and inconsistent behavior. So there are certain ways to achieve thread safety in Java, like adding synchronized keyword, which locks the critical section. So only one thread can access at a time. Then we have a volatile keyword, which ensures a visibility of changes to a variable across the threads. Then atomic classes, which performs operation without locking. And re-entrant locks, it's a flexible locking mechanism. Then we can use concurrent collections, or we can use thread confinements or immutability. So let's see one by one. So I'll be showing these examples in ID as well. So we have a synchronized keyword, so which we already seen in previous video. We can use synchronized keyword as a block or to a method. So here what's happening is, like, let's say you have a synchronized method, and the block of section, like whatever the sections will be synchronized, so that once the thread is called on that method, it will be logged for certain period of time until the execution happens. So only one thread can enter a synchronized method at a time, and it used to protect a shared resource. So you have a shared resource, and the multi-thread is acting upon it, so you can synchronize those things. Then we have a volatile keyword, which ensures visibility of shared variables across the thread. So these variables can be used for flag things, like let's say you have any a variable which is used as a flag, then you can use a volatile keyword. So here is an example. So here we have a two thread, one is writer and one is reader. So the flag you can see here, it's setting inside the first thread, that is writer thread. So inside a reader thread, what we are doing is we are checking whether thread is false or not. So if it is false, then it will execute the code. If it not, then like if it is true, then it won't execute. So what happens here is, if we don't add volatile, it might execute indefinitely. Like again, data might be inconsistent, and without volatile, the change might not be visible to the thread immediately. So then we have atomic classes, which is available under concurrent.atomic package, which provides a lock-free thread safe. So here is an example. You can see how we have used means atomic classes can be used for counter cases. Like if you want to use counter, you can go for atomic classes. So here, like no need to synchronize. It's efficient for, as I mentioned, counters and flags. So here you can see this class has increment and get a method. So this uses CPU level atomic instructions, like compare and swap, which make use of, like, no two threads can interface, and the the read, modify, read, write happens as a single operation. So compare and swap, behind the scene, what happens is, like, it reads the current value. Here you can see it reads the current counter value, then calculate the new value, check if the value is still unchanged. Then if yes, it updates it. If not, like, retries until success. So this gives, like, atomicity without locking. It's a fast and thread safe. Then we have a reentrant lock. So it's a class in concurrent.locks that provides a more advanced thread synchronization than a synchronized keyword. So reentrant means that the same thread can acquire the lock multiple times without getting blocked. So unlike synchronized, it allows manual lock and unlock system, and it also has try lock, timed lock and all. And here is example. So here you can see I have used reentrant lock, and we have lock system here. So lock and unlock. So in case of synchronize, what it happens is it will lock the block in the curly braces and unlock here after, like, at the end of curly braces. But in case of reentrant, we manually need to add the lock systems, and we have to unlock it. So before using any shared resource or critical section. So there is advanced feature like a try lock to acquire a lock without blocking forever. So you can add within if condition, and we also have a timeout as well to wait for certain time. So then concurrent collections. So it's a thread safe alternative to legacy collections. We have hash map for that concurrent hash map. Like same thing for array list. We have copy on write array list. For hash set we have copy on write array set. Then for queue concurrent linked queue. So we can use these concurrent collections, which allows read concurrent reads and thread safe updates. Then we can go for confinement. So that is use local variables. So keep data confined to a single thread by using local variables. Like it's very safe. No synchronization needed since no sharing happens. Then we have immutability. Like you can go for objects like immutable objects, which are always thread safe. And fields are here. You can see fields are final, and it's set in constructors. So no setter, no object state cannot be modified. So like choosing the right thread safety mechanism depends on your specific use cases. Like we have synchronized, volatile, atomic, and reentrant. Like all have different strengths and limitation. So when you can use synchronized in the sense like it's a simple critical section, you can go for a synchronized, and if it is read, modify, write operation, then when blocking other thread is acceptable. Then volatile, as I mentioned, you can go for a flag cases or signals. If you are using either flags or signals, you can go for a volatile. Then the atomic classes, like it's a high performance application, like you can go for atomic classes. And if you are using counter flag state management, you can go for atomic classes. Then a reintent lock, like when you need more control over locking, for manual locking, you can go for reentrant. And for complex multi-threaded requirements, again, you can use reentrant lock classes. So let's see things in IDE. So here is an example for volatile. So let me execute this first. So you can see writer thread updated flag to true, then reader thread detected flag change. So here what I'm doing is I have created a private field of flag which I set to false, and I have two thread here, writer and reader. We already seen this before that within writer block I have enabled the flag. So if it is not enabled, then the while loop will run forever. So let me remove the volatile. So now the writer thread updated flag to true. You can see then it might run forever. So let me terminate this. And if I add it back, you can see it like so the field change happened directly on the memory. So if you add it as a volatile, like as I mentioned, it will directly update the memory itself instead of for a specific thread. Then we have atomic counter here. So I am using atomic integer class. So I have initialized with the 0. So we have uh, get method as well as increment and get. So as I mentioned, it's a compare and swap process. So let me execute this first. You can see the final counter is 200 because I have created two uh, thread which will count for 0 until it is 0. It's increment and then it will come out. So as I have created two thread, it should be at 2000 because it starts from 0 to 1000. So it should be the counter should be at 1000 at for one thread, and the counter should be at another 1000. Like it will be 2000 if you add for two threads. So if I go for volatile instead of atomic, see what happens there. You might get 2000, but if you go for multiple times, it's a data inconsistency, so you might get a different value sometimes. You can see here it's not constant value. It changes, like it's not consistent. So that's why we use atomic integer. So whenever you are going for a counter cases, you can go for atomic classes. Then Java reentrant. So I have a class here called inventory. So there are 100 stocks, means I'm just trying to purchase item. So I'll be calling a for thread. So the current stock is 100, and I'm trying to buy 30 items. So the one thread should not like it should not allow to buy item for one thread. So let's see an example here. You can see first thread got executed, and 30 items got purchased. So the available is 70 now. For second attempt, the available is 40. Like after third, it will be 10. So the third, like last thread should not or it should not allow to buy the further items. So what I am trying to do here is, you can see I have an like a stock for 100. Then I'm using reentrant class, and within the method, the purchase item method, I'm acquiring the lock here. Then in the final block, so always go for a finally block. So within try, I have added the logics like purchasing the item, then checking the quantity. If the quantity is like it's available, then go for a deduction. Otherwise, say that failed to purchase and not enough stock. And once the try block is done, uh, unlock the method. And within the main method, so I have created an inventory object, and I'm using high So I'm just creating a purchase item, and I'm calling all the threads. Like I'm calling multiple threads here, like 4 threads. So if I have three threads, like it will purchase the items, like 30 items for 3 threads. But for further, it won't, because we have only 100 items. So let me execute again. You can see while attempting to purchase the third thread gave the error saying there is no stock. So this is how you can achieve synchronization or thread safety using reentrant lock. Thanks for watching.